What is rate limiter? Imagine we have a service which is receiving a huge number of requests, but it can only serve a limited number of requests per second. To handle this problem, we would need some kind of throttling or rate limiting mechanism that would allow only a certain number of requests so our service can respond to all of them. A rate limiter at a high level limits the number of events an entity, like as an entity, either it can be user, device, IP, etc., can perform a particular time window. So this entity can perform in a particular time window. For example, a user can send only one message per second. A user allowed only three failed credit card transactions per day. A single IP can only create 20 accounts per day. In general, a rate limiter caps how many requests a sender can issue in a specific time window. It then blocks requests once the cap is reached. Now, why do we need API rate limiting? A very good question. The rate limiting helps to protect services against abusive behaviors targeting the application layer, like denial of service attacks, brute force password attempts, brute force credit card transactions. So, if you don't know about brute force passwords or brute force attempts, this is trying number of combinations so that either one of them pass. And these combinations are tried rapidly, one after another. These attacks are usually barrage of HTTPS request, which may look like they are coming from a real user, but are typically generated by machines or bots. As a result, they attack these attacks are often hard to detect and can more easily bring down a service, application, or an API. Rate limiting is also used to prevent revenue loss, to reduce infrastructure cost, to stop spam, and to stop online harassment. Following is a list of scenarios that can benefit from rate limiting by making a service or API more reliable. Misbehaving. Client scripts, so either intentionally or unintentionally, some entities can overwhelm a service by sending a large number of requests. Another scenario could be when a user is sending a lot of lower priority requests, and we want to make sure that it doesn't affect the high priority traffic. For example, user sending a high volume of requests for analytics data should not be allowed to hamper a critical transaction for other users. Security. By limiting a number of second factor attempts that a users are allowed to perform, for example, the number of times they are allowed to try with a wrong password. Now, we can also use a rate limiter where to prevent abusive behavior and bad decision practices. Without API limits, developers of client application would use sloppy development tactics, for example, requesting the same information over and over again. We can also have this rate limiter to keep cost and resources usage under control. Services are generally designed for a normal input behavior. For example, a user writing a single post in a minute. Computers could easily push thousands of these requests per second through an API. Rate limiter enables control on the service APIs. Also, if this is the condition, then revenue also kicks in. Certain services might want limit operations based on their tier of their customer services, and thus create a revenue model based on rate limiting. There could be default limits for all the API service offers. To get beyond that, the user has to buy higher limits, again to eliminate spikiness in traffic, and we make sure the service stays up for everyone else. So spikiness in traffic is a burst traffic, which often comes to see when there is a flash sale. There are a bunch of traffic, and you don't want it to miss those. Now, requirements and goals of the system. Our rate limiter should meet the following requirements. There are functional and non-functional requirements. Functional requirement: limit the number of requests an entity can send to an API within a time window. Like for example, 15 requests per second. So limit the number of requests per second in a time window. Okay. Next is the API are accessible through a cluster. So the rate limit should be considered across different servers. Now this is something critical. Across different servers, the user should get an error message whenever the defined threshold is crossed within a single server or across the combination of server. And this itself can be broken down into another requirement, because we are going to notify this customer or user. There is also a non-functional requirement. The system needs to be highly available, because obviously if rate limiter goes down, it is unable to predict the system later upon. Either your system doesn't move forward, or if it moves forward, it would be exposed to hell lot of things. The rate limiter should always work, since it protects our services from external attacks. Our rate limiter should not introduce substantial latencies affecting the user experience. And this is so true. Now, how do rate limiting? How to do it? So, rate limiting is a process that is used to define a rate and speed at which consumers can access API. Okay, there is a concept known as throttling. Throttling is a process of controlling the usage of APIs by customer during a given period. So, controlling the usage of API. Throttling can be defined as an application level or API level. So, yeah, this is where you apply throttling. Throttling at API level or application level. Where a throttle limits is crossed, the server returns a status 429, too many requests. And this is a standard rate limited request, too many requests, 429. Now we have next thing. What are different types of throttling? You see, here are three famous throttling types that are used by different services. There is hard throttling, soft throttling, and elastic or dynamic throttling. So, hard throttling, as the name suggests, the number of API requests cannot exceed the throttle limit. There is a soft throttling. In this type, we can set an API request limit to exceed a certain percentage. For example, if we have a rate limit of 100 message a minute and 10% exceed limit, our rate limiter will allow up to 110 messages per second, per minute, sorry. Now we also have this dynamic throttling. What is this? Under elastic throttling or dynamic throttling, the number of requests can go beyond the threshold if system has some resources available. For example, if a user is allowed only 100 messages a minute, we can let the user send more than 100 messages a minute when the when there are free resources available in the system. Now, what are different types of algorithms used for rate limiting? And this is important. Following are the two types of algorithm used for rate limiting, and although it's not only two, there are multiple, but this is majorly two. One is fixed window algorithm, and next is the ruling window algorithm. There is also token bucket algorithm, but we'll concentrate on these two first. Fixed window algorithm. In this algorithm, the time window is considered from the start of the time unit to the end of the time unit. For example, a period would be considered as from 0 to 60 seconds. So this is one window. And for a minute, like, which means a minute. Uh, so a period can be considered from 0 to 60 seconds for a minute, irrespective of a time frame at which the API request has been made. And this is important, it is irrespective from the time when it has been made. In the diagram below, there are two messages between 0 and 1 second, and three messages between 1 and 2 seconds. So this is M1, M2, and This is M3, M4, M5. If we have a rate limiting of 2 messages a second, the algorithm will throttle only 5 ms. So we have how many? We have 2 messages a second, so a second has been passed. We have 2 messages in here. Next second, from 1 to 2, we have 2 messages M3 and M4, even though M5 kicks in, but we are not allowing it. Now the rolling window algorithm. In this algorithm, the rolling window algorithm. In this algorithm, the time window is considered from the fraction of the time at which the request is made plus the time window length. For example, if there are two messages sent at 300th millisecond and 400th millisecond of a second, we count them as the two messages from 300th millisecond of that second up to 300 millisecond of the next second. So this can be cleared here if we have two messages sent from 300 millisecond and 400 millisecond. So okay, we don't have a diagram over here. Okay, anyways, I'll try to explain this one. If there are two messages sent from 300 millisecond and 400 millisecond of a second, so 1/3 to 1/4, sorry, 300 to 400, we will count them as two messages from 300 millisecond of the second up to 300 millisecond of the next second. In the above diagram, keeping the two messages in a second will throttle M3 and M4 both. So okay, I can take a reference of this. Now it means the problem with earlier algorithm you can see over here is, even though M1 M2 came in the next window we have a slot for two more requests. But if I count my counting from this, I will assume it as 0.5. From 0.5, if I'm going from 1.5, I'm taking 4 requests per second, and that is what we don't want it. So based on rolling window, we will ignore M3 and M4 both. So we will throttle M3 and M4. So these are the two algorithms. There is also a token bucket algorithm. There is also a sliding window log algorithm, fixed window counter algorithm. So this is just a fixed window counter. But anyways, how are we going ahead with the high level design for a rate limiter? A rate limiter will be responsible for deciding which request will be served by the API servers and which request will be declined. Once a new request arrives, the web server first asks the rate limiter to decide if it will be served or throttled, and which is the first step. If the request is not throttled, then it will pass to an API server. So in this case, okay, it has its separate entity over here. Generally, rate limiter is prior to this one. So when the client hits something, it goes to rate limiter. Obviously, I'm not counting load balancer or everything, and then it goes to API server. So in this diagram, but what happens is a client sends message to web server. Web server checks with rate limiter. Rate limiter has its own backend storage, cache servers for all of its configuration and current buckets or current windows counters. The moment rate limiter says yes, I can pass or not pass, it will likewise go to the rest of API servers. So basic system design algorithm. So let's take the example where we want to limit the number of requests per user. Under this scenario, for each unique user, we would keep a count representing how many requests the user has made and a timestamp when we started counting the requests. We can keep in we can keep it in a hash table, okay, or a cache, where key would be the user ID and a value would be a structure containing an integer for the count and an integer for the epoch time. So it is clear: user ID to a structure for count and epoch time, and that is what is here: user ID, and I know it's not visible, but count start time. Cool. Now let's assume our rate limiter is allowing 3 requests per minute per user. So whenever a new request comes in, our rate limiter will perform the following steps. If a user ID is not present, oops. Okay. Now what the rate limiter performs is, if the user ID is not present in a hash table, insert it. Set the count as 1, because again I have seen it right now and the count is 1. And the start time to current time, normalize to minutes, okay. And allow the request. Why we are doing normalized to limit? Because we are doing it per minute per user. If it was second or half of the minute, so it would be likewise. Otherwise, find the record. So entire thing is happening if we find user ID within the hash table. If we don't find, sorry, but if we find the record, so we find the record for the user ID, and if the current time minus the start time, so window, this is the window. What tells us is when was the last request came in, and what is the current time. If it is greater than 1, that means you have already exhausted your limit, and set that start time to current time, count is equal to 1, and allow the request. But if the current time minus start time is less than 1 minute, so within 1 minute it has not even passed 1 minute and you're sending it again, now check for count. If count is coming greater than 3, then reject it, greater than or equal to 3. If not, increment the count and store it. It looks so simple on the paper, but trust me, when it implements into uh, distributed systems, multiple servers, you're tracking it up, it becomes complex. Now rate limiting, allowing 3 requests per minute for user Christine. So let's see the scenario. At 3 a.m. the request comes in. Now as you have seen, the Christie count is 1, start time is this. Next is a request comes at 0.1 second. No support by viewer. I guess this is not visible to us, but what would happen is it would just check whether it is within a minute or not, and it is within the minute. I'll increment the count becomes 2, and a minute has been passed, and I see what I wanted to reset the count. So count is resetted back to 1, start time is resetted to the current time. Now 1.05, I saw 1.2, 1 minute has not been passed yet, so count is incremented to 2. 1.2 to 1.4, 1 minute has not been passed yet, so count has incremented to 3. 1, 2 and 3, yeah, count is now 3 over here. And next it comes in, 1 minute has not been passed yet, but I have already hit the count 3, so I will not allow the next, because we wanted 3 requests per minute per user. So the user was Christy, and for her we saw all of this. So what are some of the problems with our algorithm? Obviously it is not a perfect algorithm. One of the problem we have seen it earlier right over here. The problem with this algorithm is this is a fixed window algorithm since we are resetting the start time at the end of every minute, which means it can potentially allow twice the number of requests per minute. Imagine if Christie sends 3 requests at the last second of the minute, then she can immediately send 3 more requests at the very first second of the next minute, resulting 6 requests in the span of 2 seconds. So we are still counting span of 2 seconds, but internally it happens within a short period of time. The solution to this problem would be sliding window algorithm, which we will discuss later. Now there is another problem with this one, which is atomicity. Yeah, which I have already touched upon, but I will see it. In a distributed environment, the read and then write behavior can create a race condition. Imagine if Christie's current count is 2 and there she issues 2 more requests. If two separate processes served each of these requests, so we have two separate servers, uh, and concurrently read the count before either of them updated, each process would think Christie could have one more request and then she had not hit the rate limiter. So process 1 can see the count as 2 and start to write, not yet written yet, and meanwhile within that window process 2 comes in, sees the count as 2, and both of them understands that hey, what I have seen is the correct, and both of them goes ahead. 2 converts into 3 by process 1, 2 converts into 3 by process 2. Ideally what should happen? 2 converts into 3 by process 1, 3 converts into 4 by process 2, but it is not happening. Now if we are using Redis to store our key value, one solution is to resolve the atomicity problem to use Redis locks, and this is straightforward. For the duration of read update operation, other thing you can use Lua script, that can be one. This however would come, again Redis scripts, this however would come at an expense of slowing down the concurrent request from the same user and introducing another layer of complexity. We can use memcached, but it would have comparable complications. Setting up memcached is by Facebook, by the way, and it would add its own complications, and again we have seen it that we don't want within our non-functional requirement user to wait much time upon rate limiter. Now if we are using simple hash table, we can have a custom implementation for locking each record to solve our atomicity problem. Cool. uh, we can do that, uh, but how much memory would we need to store all of the users data? Let's assume the simple solution where we are keeping all of the users data in a hash table. Let's assume user ID takes 8 bytes. Let's also assume 2 bytes for count, which is okayish, which can count up to 65k. Okay, is sufficient for our use case. Although the epoch time will need 4 bytes, agreed, we can choose to store only the minute and second part. Okay, which can fit into 2 bytes. Hence, we need total of 12 bytes to store users' data. So 12 bytes per user. Let's assume hash table has an overhead of 20 bytes for each record. If we need to track 1 million users at any time, the total memory we would need would be 32 MB, because 12 plus 20 bytes into 1 million. So this is an overhead, internal overhead we are taking as buffer. If we assume that we would need 4 byte number to lock each user's record to resolve our atomicity problem, we would require total of 36 MB memory, so which is okayish. This can easily fit in a single server. However, we would not like to route all of our traffic through a single machine. Also, If we assume a rate limiting of 10 requests per second, this would translate to 10 million QPS for our rate limiter. This would be too much for a single server. Practically, we can assume we would use Redis or memcached kind of solution in a distributed setup. We'll be storing all of the data in a remote Redis server, and all the rate limiting server will read and update this server before serving or throttling any requests. I can add one more thing to this point. I'm not sure whether I'm eligible for this or not, but if you're having only one server over there and you're providing 10 requests per second, obviously let's not go with a 10 requests per second. Let's take it only one request per second. You still have 1 million QPS, but again, forget about QPS as well. The point I'm worried about, this will introduce your single point of failure within your system. You don't want that. Imagine if rate limiter is down, your whole system is down. You don't want that. So again, one more upvote for Redis and memcached. Sliding window algorithm. Now this point we have seen the fixed window algorithm, where we have, where is it? Yeah, fixed window algorithm, where we have fixed window from 0 to 1 and 1 to 2. Now we are going to see sliding window algorithm. We can maintain a sliding window if we can keep track of each request per user. We can store the timestamp of each request in a Redis as a sorted set. The sorted set is a concept of Redis in our value field of hash table. Okay, what it says is to store timestamp for each request as a value field within the hash table, and that would go within a sorted set, so that I have timestamps as 1, 2, 3, 4, which is linear timeline. So a sorted set with Unix timestamp key value. Again, the user ID would be key and this would be a value. Let's assume our rate limiter is allowing 3 requests per minute per user. Again, this is the same. So whenever a new request comes in, the rate limiter will perform following steps. Remove all the timestamps from the sorted sets that are older than current time minus 1 minute. So this is generally a cleanup process. This is an improvement. So why 1 minute again? Why we are taking 1 minute? Because 1 minute is the window we are serving for. So 3 requests per minute per user. And again, count the total number of elements in the sorted set. Now how many elements do we have in a sorted set? Reject the request if the count is greater than our throttling limit of 3, and insert the current time in the sorted set as expected and accept the request. So we have only 2 options over here. So if the window which I'm seeing is the count is greater than 3, that means previous to me within the timeline I have seen 3 requests, which is within the 1 minute frame. So what I'll do over here is I'll reject it, else I will accept it and insert the current timestamp. So my timeline has one more entry of current time. Cool. Now rate limiter allowing 3 requests per minute of user Christy. How will it look like? The request at 3 a.m. Initially nothing is there, so I will go ahead, clean up the storage. The storage is already cleaned. I'll check how many count I am seeing. The count is 0 because nothing so far, and I will allow it, considering this timestamp as my first. Next is request at this timestamp. Now obviously the 1 minute has passed, so I will reject everything starting from 3.0005. I have already one entry, so I will remove that. Checking the count is 0. Shall I accept it? Yes, I should accept it. Go down. Now, time is this. Have I removed the entries? Yes, I have removed the entries. What counts do I see now? I see only one entry. One entry is fine. Accept it. Accept and store the timeline. Next one. Next one, remove 3045. So 3045, nothing is there. What count do I see? I see two counts. This one and this one. Shall I accept it? Accept it and store me. Stored. Next entry. Remove from 3050. Already removed. How many counts do I see? 1, 2, 3. Shall I accept it? No. So at this moment of time, we are not accepting the request, we will reject it, and if we are rejecting it, no point of storing this within the sorted set. The moment comes 30210 again. Now it will check for removing 30110. 30110, that means this element or this timeline has been erased from our current stream, which means we can allow this because our size is 2 now. How much memory would we need to store all of the user data for sliding window? Now let's assume the user ID takes 8 bytes. Each epoch time will require 4 bytes. Again, why 4 bytes? Because we are just curious about the last parts. Let's suppose we need the rate limiting of 500 requests per hour. Let's assume 20 bytes overhead for hash table and 20 bytes overhead for sorted set. At max, we would need the total of 12 kilobytes to store our user data. That means 4, which is the epoch time, plus 20, the overhead of sorted set, multiplied by 500. 500 because 500 requests per hour. And we have 8 because a user ID is constant for a particular user, so not including that. 20 byte overhead of hash tables and all, which would give us 12 kilobyte per user. Again, it's per user per hour. Here we are reserving 20 bytes overhead per element. In a sorted set, we can assume that we need at least 2 pointers to maintain order among elements. 1 pointer to previous element and 1 to the next element. One of the 6-bit machine, each pointer will cost 8 bytes. So we will need 16 bytes for pointers. We add an extra word, 4 byte for storing and other overhead. If we need to track 1 million users at any time, we will have this 12 kilobytes into 1 million, which means 12 GB. So 12 GBs of RAM is required for this memory. Sliding window algorithm takes a lot of memory compared to fixed window. This would be a scalability issue, which if we can combine the about 2 algorithms to optimize our memory. Yeah, we can. So sliding window with counters. What if we keep track of our request counts for each users using multiple fixed time windows? Example, 1/60th of the size of our rate limits time window. Now, for example, what I'm saying is, if we have an hourly rate limit, we can keep a count for each minute and calculate the sum of all counters in the past hour. When we receive a new request to calculate the throttling limit. If we have an hourly rate limit, we can keep a count for each minute and calculate the sum of all counters in the past hour. We receive a new request to calculate the throttling limit. This would reduce our memory footprint. Let's take an example where we rate limit 500 requests per hour. Now we are going per hour, so let's see 500 requests per hour with an additional limit of 10 requests per minute. This means that when the sum of counters with the timestamps in the past hour exceeds a request threshold. So Christine has exceeded the rate limit. In addition to that, she can't send more than 10 requests per minute. This would be a reasonable and practical consideration, as none of the real user would send frequent requests. Even if they do, they will see success with retries since the rate limits gets reset every minute. We can store our counters in Redis hash since it offers an incredibly efficient storage for fewer than 100 keys. When when each request increments a counter in the hash, it also sets the hash to expire an hour later. We will normalize each time to minute. Now this is how the flow looks like. I'll quickly overview of this one. At 3 a.m. we allow a request. The count is, so this is how the structure looks like. This is the timestamp. This is the counter. Now we have a request at 3105 and this is obviously vanished, I guess, from the picture because 1 minute has passed. Then we have 3120, we allow that. 3145, we allow that. But the moment 3150, we don't allow that. So coming back to the memory, because that's where we were concerned about how much memory we would need to store all the user's data for sliding window with counters. Let's assume user ID. User ID takes 8 bytes. Each epoch time will need 4 bytes and counter would need 2 bytes. Let's suppose we need a rate limiting of 500 requests per hour. Assume 20 bytes overhead for hash table and 20 bytes for Redis hash. Since we have kept the count for each minute at max, we would also need 60 entries for each user. So this 60 is extra. We would need a total of 1.6 KB to store one user's data. So one user's 1.6 KB, which is pretty efficient compared to sliding window approach. Thereon we go 1.6 to 1 million scale up. We get 1.6 GB roughly. So our sliding window with counters algorithm used 86% less memory than the simple sliding window approach. Data sharding and caching. So this is where we are dealing with multiple servers, distributed systems. We can shard based on the user ID to distribute the user's data. For fault tolerance and replication, we should use consistent hashing. If we want to have a different throttling limits for different APIs, we can choose to shard per user per API. Take an example of URL shortener, which we have seen earlier. We can have a different rate limiter for create URL, delete URL, APIs for each user or IP. If our APIs are partitioned, or practical consideration could be to have separate, somewhat smaller rate limiter for each API shard as well. Let's take an example of our URL shortener where we want to limit each user not to create more than 100 short URLs per hour, assuming we are using hash based partitioning for our create URL. Our create URL API, we can rate limit each partition to allow a user to create not more than 3 short URLs per minute in addition to 100 short URLs per hour. So our system can get huge benefit from caching recent active users. So application server can quickly check if the cache has desired record before hitting backend servers. Our rate limiter can significantly benefit from the write back cache by updating all counters and timestamps in cache only. The write to permanent storage can be done at fixed intervals. This way, we can ensure minimum latency added to the user's request by the rate limiter. The reads can always hit the cache first, which will be extremely useful once the user has hit their maximum limit, and the rate limiter will only be reading data without any updates. LRU can be reasonable cache eviction policy for our systems. Should we rate limit by IP or by user? This is a good question. Let's discuss the pros and cons of using each one of these schemes. In this scheme, IP based, we throttle request per IP. Although it is not optimal in terms of differentiating between good and bad actors, it is still better than not having a rate limiter at all. The biggest problem with IP based throttling is when multiple users share a single public IP, like in the internet cafe or smartphone users that are using the same gateway. One bad user can cause throttling to other user. Another issue could arise where caching IP based limits, as there are huge number of IPv6 address available to hacker from even one computer. It's trivial to make server run out of memory tracking IPv6 addresses. Now, what about user? IP rate limiting by user. Rate limiting can be done on the APIs after user authentication. Once authenticated, the user will be provided with a token, which the user will pass to with each request. This will ensure that we will rate limit against a particular API that has a valid authentication token. But what if we have to rate limit on the login API itself? The weakness of the rate limiting would be that the hacker can perform a denial of service attacks against a user by entering wrong credentials up to the limit. After that, the actual user will not be able to log in. How about if we combine the above two schemes? Hybrid approach. A right approach could be to do both per IP and per user rate limiting, as they both have weaknesses. When implemented alone, though, this will result in more cache entries with more details per entry, hence requiring more memory and storage. Everything coming back to trade offs. So, this was about rate limiting. I will see you in the next one.